Good evening. Today we're going to be talking about quantum dots in noise-resistant quantum key distribution systems. I'm Prahlad.
I'm Xiangtuo.
I'm Praneel.
Samuel.
And I'm Sumi. Initially discovered in 1980, quantum dots are semiconducting nanoscale particles measuring between 2 and 10 nanometers in diameter. Some materials of which they can be composed are cadmium selenide, lead sulfide, indium phosphide, zinc sulfide, and silicon. They exhibit unique electronic characteristics that range from those of larger semiconductor materials and individual molecules. This is due to their exceptionally high surface-to-volume ratios, which manifests in fluorescence. Quantum dots generate colors based on their particular size. This is made possible by the semiconductor crystal's radii falling short of the exciton Bohr radius, average distance between an electron in the conduction band and the hole it creates in the valence band. As pointed out by Pauli's exclusion principle, this leads to quantization of the energy levels. Due to the discrete energy levels of quantum dots, they are more akin to atoms than bulk materials. As the crystal size reduces, the energy gap between the highest valence band and the lowest conduction band widens. Quantum dots can be classified based on their structure and composition into core type, core cell, and alloyed quantum dots. Overall, quantum dots have various applications due to their various benefits their distinctive properties offer. These include their optical abilities to emit pure, bright colors, extended lifetimes, high efficiency, and high extinction coefficient. Additionally, quantum dots, being zero-dimensionless entities, exhibit a more defined density of states compared to structures with higher dimensions. Electron travel distance is reduced compared to larger particles, thereby enabling electronic devices to function at higher speeds. Quantum dots also possess size-tunable emission, high photostability, and narrow emission spectra. Quantum dots can be utilized in quantum computing due to their ability to function similarly to transistors. Information is not stored using transistors as in classical computers, but rather through individual atoms, ions, and electrons or photons that are interconnected and entangled to form quantum bits, known as qubits. These quantum scale units can hold multiple values simultaneously and process various tasks concurrently. Managing individual atoms and similar entities in this manner can be challenging, but utilizing quantum dots on a larger scale would simplify the process significantly. QKD, quantum key distribution systems, have the potential to revolutionize the way we communicate and protect our data. The development of new and more secure QKD systems can have a significant impact on a variety of industries, including telecommunications, finance, and national security. Typical public-private key cryptography is a method along with a protocol that allows one person to transmit encrypted data to another person for them to read. A private key encrypts the data. If you want to make it clear that data comes from you, use a public key to send it out into the world, and then it can be decrypted. However, if you want to designate data for only one person, encrypt it with a private key, then your public key, and the receiver will decrypt it with a private key and his public key. Public-private key cryptography has use cases in a variety of realms other than sending confidential information. For example, you can sign a document with your private key, and someone who has your public key can determine that you are the individual who signed the document. Quantum key distribution is a cryptographic protocol that similarly allows two parties to share a secret key over an insecure channel. However, QKD is based on the principles of quantum mechanics, harvesting the benefit of being unbreakable by current technology. A QKD system uses quantum entanglement and superposition of qubits to ensure a safe transfer of encryption keys for later communication. Existing platforms implement quantum-resistant algorithms, which rely on mathematical complexity to ensure security. These algorithms, integrated into cryptographic protocols, play a crucial role in guaranteeing the confidentiality, integrity, and authentication of transmissions. They are designed to withstand potential threats from future quantum computers. It is also designed to be able to detect the presence of an eavesdropper. In an open data channel, you cannot detect an eavesdropper, but in QKD, an eavesdropper must disturb wavelength, which can be easily detected.
A happy place comes in many colors. One that makes you warm and refreshed.
Quantum key distributions are important now for the same reason that public key cryptography was so important when it was invented. It provides a safe and secure method to share information, even after the development of technology. Just like plain information transfer was unsafe back then due to digital advances, public key cryptography will be dangerous after the implementation of quantum computers due to algorithms such as Shor's algorithm, which can shatter previously unbreakable information transfer techniques. As the attackers develop new technology, we must develop as well in order to keep our information safe, and therein lies the power of QKD. Additionally, QKD holds another important advantage over other quantum cryptographic methods. Its reliability is provable by the principles of quantum mechanics. Other post-quantum cryptographic systems attempt to create systems for which it is impossible to create a quantum algorithm that's capable of solving it quickly, similarly to modern cryptography. However, there's always a measure of uncertainty as to whether such an algorithm does in fact exist, and it's incredibly difficult to prove that no such algorithm does. On the other hand, QKD is based on the very foundations of quantum mechanics and does not share the same lack of rigor. This makes it a more secure algorithm. Because of these two factors, potential applications of QKD are everywhere. Wherever secure communication is required, QKD can be applied. For example, in financial services, governmental and defense applications, medical research, and protection for critical infrastructure. Additionally, QKD will undoubtedly serve as the backbone of future quantum communication networks. One such example is the quantum internet, a planned system of quantum computers that will be able to send, receive, and compute information that is encrypted in quantum states. Next slide.
Most current real-life QKD systems employ single photon emitting pulse laser diodes to send photons and detect photons using photodiode lasers. However, a limitation of this hardware is that they are very sensitive to outside environmental factors such as temperature and background radiation, all of which can cause quantum states which are emitted to be less reliable to measure. Specifically, these environmental factors can cause depolarizing, dephasing, and amplitude damping type noises to our photons. QKD is meant to be done in the outdoors over very large distances, so these environmental factors will inevitably play a big role. Additionally, even current expensive technologies still have limitations in accuracy of emitted wavelength. These factors will all make QKD less secure. Quantum dots present an alternative to these limited current hardware. Quantum dots, similar to laser diodes and photodiode detectors, can both transmit light and detect light, as well as enter superposition and entanglement, both of which are quantum mechanical phenomena that are needed in QKD. What makes quantum dots an interesting alternative is that they have less degradation to noise. Why? Quantum dots can be engineered to emit single photons with high wavelength precision. Additionally, quantum dots can operate just fine in room temperature conditions, eliminating any worries for temperature-related noise. Finally, quantum dots can be controlled to have very narrow timing jitters, meaning we can accurately control when a quantum dot emits photons.
Quantum key distribution systems hold the potential for secure communication by leveraging the laws of quantum mechanics. However,
hold on for
challenges.
just a second. Edward or David, can you mute Amy Lee?
I'm not signed in as the host. Let me try to sign in as host. Amy, if you are not the presenter, please mute yourself because it's quite rude to be making background noises while people are presenting.
Okay, thank you. Continue.
Okay. Quantum key distribution systems hold the potential for secure communication by leveraging the laws of quantum mechanics. However, challenges arising from noise and environmental interactions can compromise the security and efficiency of QKD systems. This research aims to explore the theoretical aspects of utilizing quantum dots within noise-resistant QKD systems. By leveraging advanced simulation techniques on a high-performance computing cluster, we will investigate the impact of quantum dots on enhancing the security and reliability of QKD systems. So there are three models. Firstly, the quantum key distribution model. Secondly, the quantum dots model. And thirdly, the noise model, which models spin and charge noise.
The first step to our project was to implement the standard QKD with code using the open source IBM Qiskit Python library. We modeled individual photons sent between two parties using quantum dots as standard qubits, and we were able to model photon superposition and entanglement using the Hadamard and CNOT quantum gates respectively. To ensure that our basic quantum key distribution scheme functions, we simulated the scheme using the presence of an eavesdropper without any environmental noise. After running our QKD simulation, we got back expected results, which confirms the validity of our QKD model. Later, we will combine this base QKD model with other models. We plan to make qubit and gate behavior more specific for quantum dots in our code. One of the most important integrations is that our qubit states, such as the 0 state, superposition state, and 1 state, must reflect the states in a quantum dot, which are the individual energy levels of a quantum dot. The ground state energy of a quantum dot will be the 0 state of our qubit, and we can figure out the ground state energy using the variational quantum eigensolver algorithm, which Prahlad will talk about later. The subsequent energy level of a quantum dot will be the 1 state of our qubit, and we can also find the state using our code. Finally, our superposition state will be the states that lie between the ground state and the second energy level. Finally, we will incorporate our noise model with our quantum dot model to analyze the effect of noise on the quantum dot's QKD system. We will discuss this in more detail later, but as a quick peek, we will likely add depolarizing, dephasing, and amplitude damping noises to our QKD model to stimulate the likely environmental noise factors. Next slide.
Okay, let's now talk about the QD model. Using a function we named variational form, we constructed a quantum circuit representing two quantum dots in the QKD system. This circuit, using rotation gates and parameterized by params, allows us to explore different configurations. The chosen number of qubits corresponds to the number of the quantum dots in our simulated QKD scenario. Envision the quantum circuit as a structured environment governed by the rotation gates and params as discussed earlier. These parameters introduce a dynamic element into the circuit, enabling various configurations for our quantum dots. Moreover, the explicitly specified number of qubits in this quantum circuit aligns precisely with the quantum dots in our QKD scenario. This quantum circuit, meticulously directed by the variational form function, serves as a computational canvas for crafting the quantum representation of our simulated quantum dots. At each instance of a rotation gate and adjustment of parameters, we unveil a multitude of configurations. Moving on, there's a poly dictionary that holds poly operators, acting as observables for quantum dot interactions in the QKD system. These operators define the characteristics of quantum dots. The Hamiltonian, a sum dot over poly sum op instances, provides a mathematical expression encapsulating the quantum dot system's features. These operators, in simple terms, are like detectives. So they basically observe and record different aspects of how these quantum dots behave. Spin, orientation, and other quantum features are their specialties. The poly dictionary we use essentially compiles these observations, giving us a manual to interpret the intricacies of quantum dot behavior. Now onto the Hamiltonian, which is just a sum of these poly operators. Imagine it as an equation that sums up all the characteristics we extracted from the poly dictionary. This equation becomes our roadmap as a mathematical representation of the quantum dot system's features. The Hamiltonian is the key to understanding the impact of different quantum dot setups on the stability and the reliability of the QKD system. It's the bridge between the observations we made with the Pauli operators and the practical implications for our quantum communication system. Next slide, please. Now let's see how quantum dots behave within the QKD system. Our tool of choice for this exploration is the VQE, or Variational Quantum Eigensolver algorithm, as said before by Xiangtuo. Think of VQE as a precise investigator on a mission to unveil the ground state energy for our quantum system, kind of like a detective probing the stability of quantum dots within the QKD setup. The method involves adjusting variational parameters, essentially tweaking the conditions to simulate different scenarios. It's similar to orchestrating controlled experiments to observe how quantum dots respond within the QKD framework. As we manipulate these variational parameters, VQE takes charge, meticulously navigating through the quantum landscape to pinpoint these optimal conditions. What does it bring back, though? A set of optimal parameters and the ground state energy. These parameters and these optimal parameters, they basically encapsulate specific rotations and maneuvers that guide our quantum dots into stable configurations within the QKD system. It's basically related to decoding the language of quantum dots to understand the precise combination that ensures stability. The ground state energy in this context acts as a weather glass for stability. A lower energy level signifies a more stable arrangement of quantum dots and vice versa. It's a quantitative measure of how well our quantum dots maintain composure within the QKD system. The outcomes, as said before, are the keys to unraveling the intricate behavior of quantum dots within the tailored context of QKD in order to enhance the security and reliability of quantum communication systems. So to recap, why does this really matter? As discussed before, the optimal parameters we get from VQE guide the actions of quantum dots. These parameters, represented as rotations and manipulations in the quantum circuit, set up stable arrangements. Watching how these parameters change gives us insights into preferred states and configurations that make the QKD system more stable and resilient. Optimizing quantum dot performance becomes easier when we understand variations in ground state energy, and targeting configurations associated with lower energy states improves the reliability and security of the QKD system. And basically, that is what the QD model aims to achieve in a nutshell. Next slide, please.
The purpose of a noise model is to explore sources of noise, such as charge noise, environmental noise, background radiation, etc., in order to identify how they affect QKD systems. For the purpose of our research, we use the Qiskit AIR library to create a model that explores spin and charge noise. With our noise model, we are also able to figure out potential strategies to mitigate these noises. In physics, spin refers to the angular momentum quantity associated with subatomic particles and nuclei, measured in units of the Dirac H, also known as h bar, which is the Planck constant divided by 2 pi. The spin values for electrons, neutrons, and protons are multiples of 0.5, while pions have a spin value of 0. The total angular momentum of more complex nuclei is the combined result of the orbital angular momenta and intrinsic spins of the constituent nucleons. Nuclei with an even mass number exhibit integer spin multiples, whereas those with an odd mass number have half integer spin multiples. Ground states of nuclei with an even number of neutrons and protons always possess a spin value of 0. There are random fluctuations in the spin orientation of electrons in a quantum dot. In the context of quantum computing, quantum dots are used as potential qubits, and so these fluctuations can affect the reliability of quantum operations and thus contribute to noise. Pauli errors are common errors in quantum computing and can arise from various sources, such as imperfect gates, environmental interactions, or other noise mechanisms. This is the way in which spin noise is represented in the model. Notably, the error rate associated with spin noise is tied to temperature variations, exemplifying the temperature dependency of quantum noise phenomena in our model.
Charge noise occurs when the electrical charge of quantum dots fluctuates due to external factors. Because the charge of the quantum dots is integral to the implementation of various algorithms, including quantum key distribution, it's important to study the effects that this noise may have on our system. We simulate charge noise using an error matrix that's filled with random charges, either 0 or 1. This matrix has a width equal to the number of qubits and the same height. We then extract the diagonal elements and find the mean and standard deviations of the charges in the diagonal. Finally, we create a cumulative distribution function that describes the charges. Then, we consider the probability that a distribution of random charges will be at most one standard deviation away from the mean. The idea behind this is that one standard deviation is an acceptable amount of error, while anything above one standard deviation will have an actual effect on the charges of the quantum dots and will thus cause an error in the QKD algorithm. Then we use this probability to define a Pauli error, very similar to what was done with the spin noise. The charge noise is then added to all of the qubits in the circuit. Another type of error that we chose to implement was error caused by magnetic fields. Similarly to charge noise, magnetic fields can also mess with the quantum dots in our implementation, so we have to deal with this type of noise as well. We represent the change of the magnetic field using a time-dependent Hamiltonian. Effectively, it uses the cosine function to vary the amount of influence that the magnetic field has depending on the time. This error is then added to all of the qubits by applying an X rotation gate. There are two main parameters that affect how this error is implemented, namely the number of time steps and the total time that the magnetic field lasts. The total time controls the duration of the magnetic field. If it's short, it's equivalent to a short burst of disruption, while if it's long, it's equivalent to a constant magnetic field that might be caused by external factors. The number of time steps controls the granularity of the simulation. While the total disruption is still the same no matter the number of time steps, the more time steps we have, the closer we can get to an accurate representation of the cosine function. At the end, we run the AER simulator by Qiskit, incorporating all of the sources of noise. To test, we compile a very simple quantum circuit and then observe the effects of the noise model on it to confirm that it works as intended. Later, we will use the combined QD and QKD models instead of the simple test model. Next slide.
So here are some areas of current research related to quantum dots and noise-resistant QKD systems. Firstly, starting off with single photon sources. Quantum dots can act as efficient and high-quality single photon sources, which are crucial for QKD systems. Researchers are exploring different types of quantum dots, such as self-assembled quantum dots and semiconductor nanowired quantum dots, to develop a robust single photon emitters with high photon purity and indistinguishability. Next, quantum dots, qubits. Quantum dots can also serve as qubits, the basic building blocks of quantum computers. Researchers are investigating the integration of qubits based on quantum dots into QKD systems to enhance the security and efficiency of key distribution. This research aims to exploit the unique properties of quantum dots, such as long coherence times and ease of control, to improve the performance of QKD protocols. Next, noise-resistant protocols. Quantum dots offer the potential to mitigate various noise sources that can compromise the security of QKD systems. For instance, researchers are developing protocols that can tolerate high levels of noise and loss, such as the use of quantum error correction codes and decoy state protocols. These approaches aim to make QKD systems based on quantum dots more resilient to practical limitations and environmental disturbances. Finally, integration with other technologies. To enable practical deployment of QKD systems, researchers are working on integrating quantum dots with other technologies. For example, quantum dots can be integrated with photonic integrated circuits, allowing for miniaturization and scalability of QKD systems. Integration with on-chip photon detectors and quantum memories is also being explored to create compact and efficient QKD platforms. Next slide, please.
Right now, we have the basic code for all three of the individual models, the QD model, the QKD model, and the noise model. Our remaining tasks are to combine all three of the models into one and then test its performance against a regular QKD model. The strategy for combining the three models is relatively simple. We will first combine the QD and QKD models and then layer the noise model on top of the other two. All the noise model does is define noise to add to a pre-existing quantum circuit, so it's going to be pretty easy to incorporate that one into the other two. Combining QD and QKD will be a little bit more complicated, which is why we are planning to focus the bulk of our efforts on this front.
And here are our citations. Thank you, ASDRP and Dr. McMahon. Any questions?